Good afternoon, everybody. It is 11 o'clock, so we're going to go ahead and get started. We do still have some people filtering in, so we'll get a little bit of an introduction here first. My name is Sean Maurer. I'm a mechanical engineer with the Smart Energy Design Assistance Center. We are a group housed at the University of Illinois in Urbana-Champaign, and we've partnered with the Energy Office with the Illinois EPA to offer free energy assessments for wastewater plants. What we're presenting today is just some findings that we found from our time in the field working with operators and plants on the impact that some of the efficiency measures have on wastewater plant operations and potential energy savings for your operating budgets. During our presentation, if you have any questions that you would like to ask, if you hover, I believe at the bottom of your screen, there is a Q&A window. If you'll enter your questions there, I'll be able to see those pop up. If you put them into a chat, I might miss them. So if you do have a question, put it in the Q&A window, and I'll be able to get to those. Before we get started here, I wanted to launch a poll and just see who all is joining us today. So what branch of the water industry are you in? Are you an operator, director, consultant, city official? Just figure out who's joining us today. This presentation is going to be recorded, and we will upload it to our website at cdac.org. We have a wastewater page there where you'll be able to find this presentation afterwards if you want to download it, review it later, or share it with others. We are also offering continuing education units for wastewater operators and engineers and others that need professional development hours. If you will let us know, we can email out a certificate of completion once this presentation is complete. We'll be getting those out towards the end of the week. If you're attending and you have multiple people attending with your this webinar in an office setting or conference room, if you could email our outreach coordinator. Her name is Cassie Carroll at Cassie, C-A-S-S-I-E at cdac.org. And just email us the names of all the people who are in attendance with you, and that way we can ensure everyone gets a certificate of completion and can track their credit hours. All right, so it looks like we got a nice mix of people here, a lot of operators, some consultants, wastewater directors. Okay. Still got some people trickling in, so I'm going to leave that poll open off to the side, and I'll share the results in a bit here. But as people continue to filter in, if they could continue to just let us know who's here, it'd be nice for us to keep track of. So about our program, CDAC has partnered with the Illinois EPA Office of Energy and the Illinois Sustainable Technology Center to help local municipalities reduce their wastewater treatment costs. We do a free energy assessment. And after that assessment, we will offer a comprehensive report that will cover potential measures that we found for your plant, the potential energy and cost savings for those measures. We'll estimate project costs and payback periods, give you some economic analysis, and we'll list any applicable incentives and some funding opportunities to help fund those projects and help move those projects forward. After we've delivered that report to you, we'll also be in touch to see if any of those measures are going to be implemented at your facility, and if you need any assistance with finding funding or anything else. To move those projects forward. So we're going to end our poll right now just because it's kind of blocking the screen. We can see there who all is attending today. So again, we are offering those assessments free to publicly owned wastewater treatment facilities. And we do provide a full report with full details of the measures that we're looking at. The CDAC office is a public-private partnership. Our goal in the state of Illinois is to reduce the state's carbon footprint. Um, and this wastewater program is one of the programs we offer to help achieve that goal. Moving on to how we kind of benchmark our wastewater facilities and see where we're at. We have assessed currently somewhere around 55 facilities in total. You can see scatter plotted here the facility types, coarse bubble, fine bubble, lagoons, and what their energy consumption profiles are. On the left-hand side of the screen is total electric consumption relative to population equivalent for the plant. Obviously, the larger the plant, the higher the flows that come into the plant, the more energy usage it's going to consume. The goal of our program is to offer energy efficiency measures that are going to try to flatten this curve and reduce the slope of that line. You can see that the trend here is almost a 45-degree angle up through the chart. Through adding more efficient motors, VFDs, capacity control, we can start to bring the slope of that line down. On the right-hand side of the screen is an energy intensity chart. We've looked at a lot of research papers on how wastewater plants are benchmarked. There are a few different ways. What we've chosen to show here is the electric consumption per million gallons on the y-axis and the gallon per person or population equivalent on the x-axis. And it shows a bit of a logarithmic trend. Most plants we tend to find are designed somewhere around 100 to 120 gallons per person or population equivalent. So you can see a tight cluster right around there. Plants that tend to have a higher gallon per person equivalent tend to have either a large industrial customer that's adding wastewater to their flows, or I&I issues. We tend to see a lot of plants that have stormwater basins and control methods for stormwater flows tend to have a higher gallon per person equivalence. Because they've got stormwater coming into the system and increasing flow rates to the plant relative to the population they're serving. The higher up you go on that chart is higher electric intensity. Usually we see that for smaller plants. Economies of scale do apply for plants. So you notice that lagoons are really high on that list, mostly because those tend to be constant aeration processes and constant pumping processes. They don't have a lot of scalability in their operations, and so they tend to be higher consumers of electricity per million gallons. Another way to display this chart, and has a similar profile, is to display kilowatts per BOD loading rate. And we're working on developing that right now for the plants that we have data for. And hopefully we'll be presenting that in our future reports. We do include this benchmarking data in our reports to give you an idea, once you receive a report from us, where your plant stands in relation to other plants in the state. And we try to break down where you are as far as energy intensity ranking. We'll give you a table of those benchmarks and let you know where you stand as far as energy efficiency and overall operations. Some of our top energy recommendations. For most plants, aeration is the largest consumer at the plant, so we tend to focus on aeration optimization through fine bubble diffusers or on-off controls of aeration, anything that can minimize the impact of how much energy needs to be added to add oxygen to your process. Coupled with that are blower upgrades and controls. If you've got an aeration process that you cannot back off the airflow when you don't have as much demand, then you're going to end up over aerating that process and wasting that energy. So those two kind of go hand in hand, and because it's such a large component, it is a big focus for our program. The next thing is wastewater pumping and recirculation pumping. So electric motors and motor controls like VFDs are another frequent recommendation for our projects. This is a chart just showing the count of recommendations for the reports that we've sent out. You can see lighting is a very, very common one. It's common because it's a low cost recommendation. Almost every plant gets at least one lighting recommendation measure. LEDs are an easy swap out for most plants, and they pay back relatively quickly, usually within 3 to 5 years, depending on the type of lighting fixture that's being recommended. VFDs is another very common recommendation. Applies to pumps, applies to pump lift stations, applies to aeration processes at the plant. Um, Aeration and blower upgrades, right sizing of blowers to match demand. We typically find a lot of plants are oversized because they're planned for population growth, but then their current operation isn't at its best efficiency because they're usually not meeting that design flow rate, that design loading. Um, and so including blower upgrades or ways to stage that blower capacity to match your demand is a frequent recommendation as well. Our aeration category there on the far left, usually that recommendation is some kind of improved distribution, either fine bubble diffusers or some kind of staging of the aeration system, cycling through oxic, anoxic stages, some way to minimize the oxygen demand in the system and minimize the electric consumption for that process. This chart is showing, of those recommended measures, what the total estimated capital cost for the measures that we've recommended is, and what the total estimated savings are is in green. What I want to point out is there's a factor of 10 difference between the cost columns and the savings columns. So if they're approximately the same height, overall on average, it's about a 10-year payback for those measures. So again, looking at lighting, one of our most frequent measures, the costs are low, the savings are relatively high to that cost, so that payback is usually about 3 to 5 years. Motors is another common one. Upgrading to premium efficiency. Again, that payback for really large motors usually pays back within somewhere between 8 to 10 years. VFDs, again, very common recommendation, significant savings, slightly less than 10-year payback, usually somewhere around 8 to 10 years for those as well. The one thing I wanted to point out here is alternative energy sources. Even though that's a really high cost measure, it is a high payback as well. Things like CHP, solar panels, if your plant can make use of those, you can also get a lot of extra benefit as far as funding for those, because there are a lot of programs that help move plants towards net zero energy and reducing their impact on the electric grid. Excuse my dog barking in the background there. DO controls is another very common option for our recommendations, pointing out again there that aeration costs, that payback is usually somewhere in the 7 to 10 year range. Getting into some of the specific measures that we usually recommend, again, one of our most common, aeration upgrades, upgrading from coarse bubble to fine bubble diffusers. Those fine bubbles are going to increase your oxygen transfer efficiency and thus decrease the amount of air you need to add to your system, and decrease the electric generating capacity you need to have to produce that aeration. Smaller bubbles rise slowly, so that also increases oxygen transfer efficiency. Typical savings is somewhere between 20 and 30% of your aeration energy is what we usually see. Some influences on that potential savings is whether you've got a continuously aerating process versus a variable one. Usually we see variable aeration with aerobic digestion after the aeration process. Sequence batch reactors, those are going to slightly reduce your savings potential. If you've got continuous 24/7 aeration, specifically if you don't have DO controls, you're going to see a lot more potential savings from switching to a fine bubble system, mainly because you can then couple those systems with controls and see additional savings. One thing to be aware of when swapping to fine bubble is because they don't rise as fast and they don't have as much surface area rising through the water, they do have a slightly reduced ability to generate mixing. So some facilities, depending how they're designed, will need to add supplemental mixers to their systems. That way they maintain solid suspension and continue to, sometimes some plants have used pulsed aeration to generate mixing, so the fine bubbles will have higher pressure sent through them and transition back to a more of a coarse bubble for mixing temporarily, and then go back to an aeration standard pressure and return to a standard aeration process. Adding a small mixing motor to the system is a little more energy efficient than doing pulsed aeration and increasing that oxygen and air input to the water. But it is something to be aware of if you're swapping to a fine bubble system, is that you're going to have some consideration for mixing of your system. Another thing to consider is that the finer pores on a fine bubble system are more prone to clogging. As you build up scum on those diffuser plates and openings, it will transition back towards more of a coarse bubble operation, and you'll start seeing a reduction in oxygen transfer efficiency. There is a slightly higher maintenance cost to using fine bubble. There are certain diffusers that use EPDM membranes that as the opening starts to get coated with scum and start to close off, it's a flexible opening, so it can open back up and maintain its original size. So there is some consideration there as far as what you put in. Those EPDM membranes are typically a little more expensive than the fine bubble ceramic plates and things. If you do upgrade your blower system to a fine bubble system and you're reducing that airflow that you need, you may also need to consider downsizing your aeration blowers or adding VFDs to them. Depending what your blower system is, that could be a significant additional cost to your system to maintain operational efficiency. With centrifugal blowers, typically you've got a minimum turn down that's limited by pressure requirements in the system and heat dissipation requirements. With positive displacement blowers, typically you can get a little bit more turn down, so they're maybe not as prone to this issue as centrifugal systems, but it is something to be aware of, especially with large aeration systems. If you're upgrading a full basin, smaller plants maybe not as much of an issue, but something to be aware of if you're doing upgrade projects, that there may be some additional hidden capital costs as far as requirements for supporting systems like your blowers. And usually when we write our reports, we try to include those details for you. One of the things we see a lot of plants, as I mentioned earlier, they tend to be oversized in planning for future population growth. What that tends to lead to is for blower systems that are oversized, you see throttling on those systems. You can see here an example of a multi-stage centrifugal blower system with butterfly inlet valves. While that does provide some energy savings through reduction of mass flow through that blower, it's not as efficient as putting a VFD on that system and slowing them down. Again, the consideration there is you can only slow down so much and still maintain your distribution pressure requirements and your heat dissipation requirements for those motors. Something to consider if you are going to be resizing your system, you can obtain higher efficiency by reducing the size of those blowers. If you put in smaller blowers and put in multiple units, you add some redundancy to your system, which can help with maintenance, can help prevent maintenance shutdowns of the process because you have supplementary backup units that can maintain process loads. You'll also maintain higher efficiency of those individual units because you can operate them closer to their best efficiency point more consistently. Typically, we see savings potential from resizing units and right-sizing units somewhere between 5 and 10%. If it's just a standalone resizing without additional controls. If you then add VFD operations to those, that savings potential can increase significantly. Another thing, older motors are reduced efficiency compared to modern systems. I know the standard right now is NEMA premium efficiency. Typically those are 3 to 6% more efficient than standard old high efficiency or standard efficiency motors. They have a much longer service life because they're made with better materials. There are upgraded motors now called super and ultra premium that meet IE4 and IE5 standards from the International Electric Agency. Um, and those offer an even further improvement and of 1 to 3% on the efficiency of those motors over NEMA premium. Um, they are a little bit more expensive. I know the IE4 motors are designed to be cost competitive with NEMA premium. The IE5 are a little bit more expensive than that. Um, but again, with better materials, with better windings, better, smoother bearings, on top of the energy efficiency increase that you're going to get from those systems, you're also going to get a maintenance durability increase. Um, so on top of improving your energy efficiency, you're also going to be reducing your maintenance hours on those systems. Moving on to one of our most common measures, lighting upgrades. LED lighting can cut lighting power up to 50% depending on your fixture. There's a significant reduction in the maintenance of those lighting fixtures because once you put in an LED, it's typically there for 10 to 15 years before you have to replace that fixture. If you do install LEDs, one of the things we find with exterior LEDs is they have individual built-in photocells a lot of times per fixture. One of the things we notice is that traditional thermal sensors are prone to failure. We see a lot of these within a couple years that sensor has failed and the lights are on in the daytime, which is an energy waste. There are new electronic photocells. They have a 10 to 20 year service life. It's a slightly different technology, but works the same way. It's just a photo eye attached to the fixture. But the lifespan of that photocell is going to match the lifespan of the bulb of the LED fixture. So when you're specifying LED lighting and upgrades to your lighting systems, one of the things to consider is that that photocell is specified to be one of the longer life units. Another thing we've found at a couple of plants, since most wastewater plants have security fencing around them, a lot of plants are operated on a day shift operation or a 2-shift operation. There are times when the plant is unoccupied at night. Unless there is a specific ordinance in your area for lighting, outdoor lighting for security purposes, we've seen a couple of plants that just, they've got a common switch either at the admin building or some location at the site, and they just manually turn off the lights. If they have to be there at night, they'll manually turn them on. Then you don't have to worry about sensor failures. You don't have to worry about maintenance of those systems. It's just a manual switch. So that is an option that we've seen in some locations. Maybe not applicable everywhere, but it's something to consider. And it's a significant energy savings on exterior lighting over letting it run on a day dusk to dawn sensor. If you do have to put in a photocell, just a couple of notes: located out of direct sunlight, you want it to pick up ambient light. A lot of photocells can be tuned that way, but you don't want it in a dark shaded area that's not going to pick up any light at all. So for example, this wall back, if you put it on a photocell common to this on the opposite side of this is a south facing wall. If you put it on the north facing wall or the north slope of the roof, so it's not in direct sunlight, but it's not in total shade either, that's a good way to extend the life of those occupancy sensors. If you can use one common sensor instead of a sensor per fixture, again, you're knocking down the maintenance load for maintaining multiple photo eyes. And it's a little bit easier to just replace that one fixture than, say, 3 of them fail at once. Another option is to back up your photo eyes with a time clock or a SCADA control system that's programmed to do dusk to dawn control of the lighting. That way, if a sensor does fail, you've got a time clock system that can then turn that light off during the daytime. Capacity control is a very important thing for a lot of plants, and we'll touch on this a little bit later, but if you've got inflow and infiltration issues at your plant, we've done a little bit of research on what kind of energy impact it has to reduce those flows, and what we find is plants that have the ability to do capacity control have greater energy savings from reducing flows to the plant than plants that run at a constant basis. Obviously, if you can adjust your system operations to match flows coming into the plant, there's a significant energy savings there. On top of that, it reduces motor wear, bearing wear, shaft wear from stop-start operation. Um, it creates excessive heat in the motor, which gradually wears down insulation on the windings. Um, Bearings and shafts from stop-start operation see higher torque, higher loads on those, which increase wear on those over time. Another consideration um, is fluid slugging through your system. If your pumps kick on and off, you get a sudden jump in flow rate through your process that sends a slug of influent into your process that can potentially disrupt momentarily your biological processes. And if you add a VFD to pumping systems and aeration systems, you're better able to maintain operation closer to the best efficiency point operation of those pumps and aeration systems. Much better than if you're doing throttling of flows. It adds a lot of process flexibility and decreases maintenance overall. On pump controls, we see you can do pressure related. Most commonly, we see wet wells with level-based flow controls. They can also be based on flow measurement. If you've got a partial flume or other flow measuring device that can stage and adjust the speed of pumps. One of the things to be aware of especially for lift stations, if you've got a high head pumping system, your savings potential is going to be at the lower end for VFDs because the head pressure requirements are going to put a limitation on how much speed reduction you can have for that motor. Usually what we see for high head operations is that pump speeds are limited to somewhere around a 20 to 30% turn down, where if you've got a standard operation, you can see turn downs up to 40, 60% of pump speed. Typical savings, the low end for high head, somewhere around 10%. The upper end, 20%, is typically for standard operation pumps like RAS and WAS pumps. For aeration systems, there's a strong dependency on temperature and humidity for optimizing airflow. Increased temperature and increased humidity decrease the density of air passing through that system and increase your power requirements to deliver oxygen to your aeration process. So we do see a lot of times, especially with centrifugal systems, the temperature and humidity in the space put a limitation on how much turn down in the summertime in particular aeration motors can have for VFD operation. Another limitation is surge. You can only back off the airflow in a centrifugal system so far before you hit a condition where air will slug out and then backflow into the system. And it creates a lot of maintenance issues, can damage that system, and it's going to disrupt your aeration process. But if you can put a VFD on your aeration system, we typically see savings anywhere from 20 to 40%, depending on what the previous operation of the system was and what type of blower is installed. If you've got a positive displacement blower system, like a rotary lobe or a screw system, one thing to be aware of for those is your savings are going to be linear. So if you back off your airflow by 20%, you're going to see a 20% reduction in savings. Whereas with centrifugal systems, it's a cubic relationship. A 20% reduction is somewhere around a 50% reduction in power. So something to be aware of there. Centrifugal systems will see much greater reductions from a small speed reduction than positive displacement systems. One final note on capacity controls. We were hoping to have the City of Galena's operator or city manager talk a little bit about how they developed this process. But they've got two oxidation ditch processes, and they turn on one oxidation ditch when their flows exceed the capacity of a single operating ditch. So what they've got here are 40 horsepower motors driving a surface turbine aeration system. Those rotors are on VFDs. Usually the one oxidation ditch runs the plant without issue until they have a storm event come through, and then they turn on this second oxidation ditch. because of this capacity control, that's 80 horsepower in total that they're just shutting off and not using when they don't need it, instead of running both ditches at a reduced rate. So there's some significant energy savings potential we see here. We've also seen plants with oxidation ditches turn off just one of the rings on the oxidation ditch. Um, Sequence batch reactor plants have kind of an inherent staging capacity built into them as well. You only turn on the reactors that you need to handle the flows to the plant. It's a little more difficult to set up with continuous aeration basins and other processes, mainly because you have to reestablish colonies of microbes in those systems. But any way that you can um, instigate some kind of capacity control for your system is going to introduce a whole lot of potential savings. Um, we've seen up to 50% reduction in power requirements just from capacity controls like this, where you're enabling or disabling a whole train of processing equipment. Automation helps a lot with this. It's very difficult to manually stop and start a process, but with computer controls and automated valves, flow gates, it's a little bit easier to tune these processes and operate them without disrupting your treatment processes. And the nice thing about this is if you can implement it at an existing plant, it's not a capital improvement. Depending on the difficulty of setting it up through your automation system, your SCADA system, it in some plants it is potentially able to be done manually. I know I've seen an oxidation ditch plant that was manually able to do this kind of capacity control. But it's free energy savings. So if you can look at your plant processes and find some way to do some kind of capacity control like this, it's an excellent way to generate savings for yourself and reduce your operating costs. Now we're going to get into the big ticket item, inflow and infiltration impacts. I know every agency is well aware of inflow and infiltration coming into their plant and the impact that can have on their processes. Increased flow rates of clear water coming into the process can flush out microbes and disrupt your treatment process. There's the increased energy from pumping. A lot of plants have storm overflow processes separate from their treatment process, so you've got separate holding facilities that have to be started up. And so there's a lot of different varying ways to handle I&I flows, but they all have increased energy impacts for those plants. On the left side of the screen here, you see this was a plant that condensed 3 different wastewater treatment facilities into one regional facility. Because all those flows were coming to one place, they had to build, I think this was an 18 million gallon stormwater retention basin highlighted in red there. It's a whole extra capital cost that maybe if there was a pre-existing I&I assessment on their system, they could have invested that into reducing flows coming to the plant. So we're working on a report right now to try to assess what energy impact I&I flows have on a statewide basis, and then how plants on an individual level can address I&I cost effectively, looking both at energy consumption and process disruptions. You can see on the right side of the screen here, that's me in a grit screening chamber. It's a below ground screening chamber that when they have inflows from storm events, it floods the screening chamber. You can see the red line there is denoting where the water level was the day before we went and did this site assessment. Major problem here is you've got a grit separator there that you're flooding that motor in that system. There's potential there for damage to that equipment. As the water increases, you're then bypassing that screening system, so you've got greater potential to clog those pumps, things like that. And again, you've got this surge of clear water going through. This was a standard activated sludge system that has the potential to then flush out the microbes and disrupt that treatment process. So addressing I&I can be a significant, have a significant impact on reducing your energy consumption and your operational budgets. This is a flow chart for a water plant that had two different stormwater bypass control, uh, depending on how much flow is coming into the plant. So as you follow through the process there, the first flow diversion there for storm flows is to direct through a primary clarifier and then out to an excess flow storage basin. From there, once flows are reduced and the disinfection system can handle those flow rates, then they just pump that settled and cleared water to disinfection and out to the outfall. For further increased flows, they've got a secondary set of excess clarifiers. And again, those treat those flows, reduce solids as much as possible, send it through disinfection and the outfall. The thing here that I want to point out is that those storm flows are bypassing the bulk of their treatment process. And so there is a potential here for reduced effluent quality going out to that outfall stream. So it's important here to note that there's also water quality impacts on top of energy impacts for I&I processes. Another thing to point out is I&I flows can push your process off your best operating point for your overall process, very similar to how throttling pushes your system curve off of a pump's best efficiency point, which is what's shown in the bottom diagram there. Most operators know that there's an optimal point of operation for their plants, and they work to maintain that optimal point of flow, food to mass ratio. But I&I flows throw those off, enforce some additional labor hours, additional processing systems, additional separation systems, in order to maintain that operating point for your plant. So the main point here is that, if you can address inflow and infiltration and maintain consistency coming into your treatment plant, you're going to improve the water quality coming out, and you're going to reduce both energy consumption, maintenance of additional stormwater processing systems. So there's multiple impacts there that stack up and provide benefit for addressing inflow and infiltration. We kind of zoomed through that presentation. If there's any questions that anyone has on anything that we've contained, I'd open it up for questions now. Please enter those in the question and answer section. Again, we are offering continuing education credits as well as professional development hours. If you have multiple people attending this webinar, email Cassie there. Her contact information is on the right, cassie@cdac.org. If you have any follow-up questions for me, you can email me at spmaurer@illinois.edu, and I'll be glad to follow up with you after this presentation. Also, this presentation will be, it has been recorded, will be uploaded to our website so you can review it in the future. If anyone has any questions, I would open it up for questions now. We did have someone in the chat ask a question. Have you seen VFDs used on exhaust fans to control velocity based on wind conditions? I have not seen that, but it does bring up a point for ventilation systems. One recommendation that we have offered for a couple of plants that didn't have it is hazardous gas detectors to control ventilation rates. And there are significant impacts on the ventilation energy consumption and heating and cooling loads for those spaces. So that is another measure that's starting to become more frequent for plants that we visit. But no, I haven't seen VFDs used to compensate for wind conditions. That's an interesting concept. Do have a question about EPA grants for facilities. There are a few different grant opportunities. There's the State Revolving Loan Fund. That is one source of funding that's offered on a continuing basis. There is also associated with this program, there is a funding opportunity It's closed for 2020, but we're anticipating that it will be renewed for 2021. Um, the funding rates are flexible, depend on your project. Um, I don't have specific details because it fluctuates a little bit for each program year. Um, but yes, there are EPA grant opportunities that come up periodically to help fund these kinds of projects. Does CDEC provide assistance to apply for grants and incentives? Yes, we work directly with ComEd, Ameren, um, so we can put you in contact with the coordinators for those. We also, in our reports, will list potential incentives from those utilities. We also have a whole section of the report that lists different funding opportunities, such as the revolving loan fund. Um, there's also some funds in there for net zero planning for plants that we list in our reports. So we do have that material. Also, if you just want that information directly, please feel free to reach out to us and we'll just pass that information along to you. What types of measurement instrumentation do we see for blower air? Usually we'll see a static pressure for the header, and then distribution out to individual basins will be controlled by a throttling valve, and that valve is controlled by a flow sensor and a DO probe. So the DO probe is going to measure the oxygen requirement. That's going to get converted into a CFM measurement. That CFM measurement gets reported to the control valve, which will then throttle airflow to that individual branch, to that basin. That creates back pressure onto the main header. That pressure, that static pressure in that header, is then what goes into controlling the VFD for the blowers. It's typically the way we see that done. There's also a DCEO grant opportunity for infrastructure that's due June 30th. Going back to the question about funding opportunities, Cassie posted a link in the chat for people to look at. Again, if you're interested in having us look at funding opportunities, let us know, sign up for an assessment. We'll be glad to do that for you. There is a question, is there any new invented equipment in wastewater treatment plants to help conserve electrical energy? There are a lot of processes now with the focus on biological nutrient removal and doing that most efficiently. As far as new equipment, it's mainly focused around process operations at this point. There are some new equipment. We can do further research into that if you have anything specific in mind. But we've looked at, for smaller plants, there was a completely air-driven pumping system that had kind of natural flow recycle from the a clarifier section, but it's for very small flows up to 300,000. But it had very low energy intensity for that system. We've also looked a lot at there was a system called the algae wheel, which is essentially a rotating biological contactor system. Those systems are very, very energy efficient. There's an EPA report that, depending on whether they're motor driven or air driven, they're 30 to 50% more less electric consumption than standard activated sludge systems. The one thing we do note is that historically, the rotor arms and axles and bearings for those systems have had maintenance issues in the past, and so in the 80s or so, rotating biological contactors started falling out of favor in favor of activated sludge systems. But they are making a resurgence now, mainly because they are there have been improved manufacturing of those systems, and they're highlighting that they are very energy efficient, especially for BNR processes. Question about solar power incentives and assisting with solar power funding. Yes, there are incentives for solar power. There is a net zero energy grant. I cannot remember it off the top of my head. Clean Energy Foundation. Plants that are implementing plans to get to net zero energy consumption installing solar. CHP systems are included in that as well. There isn't a grant incentive for those. You can work again with ComEd and Ameren. They can supplement those grant opportunities. And so there are incentives for almost everything you can think of somewhere. And we can help find those and help you apply for those as well. What do I recommend for energy monitoring? I've seen a couple different methods of linking energy monitoring to SCADA systems. One is a calculated power draw for systems. So an engineer that's programming the SCADA system will enter in information about the installed horsepower of equipment, VFD installed on that, and then calculate both power and energy draw from those systems. I've also seen it done with direct metering of those, sub-metering of those systems. So an electric meter can be installed and report back to the SCADA system to build a benchmarking. And I would recommend that. Energy monitoring can help identify problems in a system. Long-term tracking can help track whether your process is slowly increasing in energy use. If you see a sudden jump, you know to go out and look for some kind of mechanical failure. If you see a sudden drop, might be the same thing. Something may have dropped offline. So energy monitoring is a great way to track the performance of your system over time. And I would recommend it if you can do it. I had a couple questions come up in the chat. I want to scroll back through and try to find those. Have I seen VFDs? Okay, so that was the exhaust fan. If anyone on the call is interested in pursuing these opportunities, looking for funding sources, kind of a generalized assessment on energy conservation opportunities, what their plant can do to upgrade, reach out to us. There's an application at www.cdac.org/wastewater. Fill out that application, get in contact with us. We'll come out and do an assessment for you. And we will we'll get you information on those funding opportunities. It's all included in our assessment reports. Does the assessment cost anything? Our assessment is offered free through our partnership with the EPA Energy Office. So no, when you sign up with an assessment for us, there's no cost to you for that assessment. We will coordinate the time to come out and do an on-site assessment. Right now, we're even doing remote assessments. We've done remote assessments for a couple of plants and are working on those reports now. So that's also a potential. So that now is a great time with the stay-at-home order to start planning for. There will be government incentives coming out to help reinvigorate the economy, and we're anticipating that some of those are going to be directed at capital projects and funding projects. So now is a really good time to contact us. We can come out, do an assessment for you, and start planning for capital projects and making use of those recovery funds. So we can help coordinate that as well. I don't see any further questions in the chat or the Q&A. If that's the case, there are no further questions. And I will thank everyone for attending today. I hope our session was informational and helpful. If you do have any further questions after this, feel free to email myself or Cassie at our email addresses there on the screen, and we'll be glad to get in touch with you. Thank you all, and have a wonderful afternoon.